Good afternoon and welcome to my last brief video lecture for Philosophy 4400 about quantum mechanics. This is going to be just a brief lecture about three other interpretations of quantum mechanics. We talked in some detail about the Copenhagen interpretation and Bohm's interpretation, and these are going to be three other possible interpretations. The first is the Grw theory, otherwise known as the spontaneous collapse theory. This is named after the physicists Girardi, Ramini, and Weber. And the motivation for this had to do with the problems with the Copenhagen interpretation. The Copenhagen interpretation postulates a wave function collapse, which is caused by observation or measurement. And many physicists and philosophers think there's something very problematic about this, about giving a special role to observers. And that raises questions about what is so special about an observer, or what exactly is an observer, or what exactly is a measurement or measuring device, and how do they have special physical properties. So this is an answer to that. GRW have the idea that there are spontaneous wave function collapses which can occur for any particle. So there's nothing special about measuring devices or observers. Now, in the case of an individual particle by itself, it has an extremely small probability of collapsing within a normal kind of human time scale. So if you just have a single particle, you should basically never expect to actually observe a collapse during your lifetime. However, if you have a large collection of entangled particles, and what this means is basically they're particles who their state is correlated with each other. So in a way that's like the two particles in the EPR experiment where the two electrons have a correlated state. Okay, so that can happen for a large collection of particles. And an example of that is an ordinary macroscopic object. The locations of all of these different particles in a macroscopic object are correlated with each other. So if some of the particles move, generally the whole macroscopic object moves. So the theory is that if a wave function collapse occurs for any of the particles in this system of correlated particles, then it induces a collapse for the entire system. And so you can adjust the postulated probability of collapse so that even though you should never expect to observe a collapse for an individual particle, if you're only observing a one particle system, you should never expect to observe a collapse in your lifetime. Wave function collapses should be expected to occur constantly for macroscopic objects. And that's because macroscopic objects just have enormous numbers of particles in them, like on the order of 10 to the 23rd or more particles. And so ordinary macroscopic objects, you never expect to see them in a superposition for any noticeable time period. They're going to constantly be in definite states. And so that's supposed to explain what we observe. The fact that you can get these apparent superpositions when you're dealing with small numbers of particles, but ordinary macroscopic objects are always observed to be in definite states. Okay, now the second interpretation that I want to mention is the famous many worlds interpretation. This derives from Hugh Everett and Bryce DeWitt. And they had the idea that when a system goes into a superposition in its quantum state, what actually happens is that the world splits into two or more worlds. So if you have a superposition of two different states, then there are actually two worlds, one world in which each of the states that's in the superposition occurs. This avoids having to have a wave function collapse, and so then you don't have to answer questions about what induces the collapse and why observers and measuring devices are so special. So for example, if you have a y-spin up electron and you feed it into an x-spin box, thereby measuring its x-spin, what actually happens according to Everett and DeWitt is the world splits into two worlds. There's one world in which the electron comes out being x-spin up and another world in which it comes out being x-spin down. And in the first world, the observers in that world see the electron to be x-spin up. In the other world, they see it to be x-spin down. Okay, now a couple of questions about this. You might ask, how do you recover the probabilities that are predicted by quantum mechanics? Because quantum mechanics gives you a certain probability of having a given measurement outcome. In the many worlds interpretation, every measurement outcome actually occurs. It just occurs for different observers in different worlds. So to explain where the probabilities come from, you have to say something like, well, the world splits into many different worlds, and the probabilities given by quantum mechanics are the proportion of worlds in which a given measurement outcome occurs. So if quantum mechanics predicts that a certain measurement outcome occurs if quantum mechanics predicts a 50% probability of a certain measurement outcome, then what that means is that it occurs in 50% of the worlds. Okay, now in the case where the probability is 50%, you only need to have two worlds in order to get a 50% probability. But if the probability is 2/3, then you need to have at least three worlds. But in general, in quantum mechanics, the probabilities can have real numbered values. So in order to get real numbered probabilities, you have to have a continuous infinity of worlds, and then right? So if the probability is, square root of 2/2 or something like that, then you have to have this continuous infinity of worlds in order to have that proportion of worlds in which a given measurement outcome occurs. Now, a problem for the many worlds interpretation that David Albert discusses in his chapter 6 is what he calls the preferred basis problem. This is the problem that actually every quantum state is a superposition relative to some observables, and it's a definite state for some other observables. So to explain what I mean, take the example of spin. If you have an electron that is y spin up, then it's in a perfectly definite state for y spin in the y direction, but for spin in the x direction, it's in a superposition, because the state y spin up is just identical to the superposition of x spin up and x spin down. And so if an electron gets into this state, is there a split into two different worlds or not? Does it split into two different worlds because there's one world where it's x spin up and another world where it's x spin down? Or is there just one world because it's in a definite state of y spin, so just one world where it's y spin up? All right, so in order to address this, you would have to come up with some preferred basis. That is, you have to come up with the preferred set of states such that when you get in a superposition of states of that type, then the world splits. Okay, now this problem led David Albert to put forward a different theory. And this is the third theory, the third interpretation of quantum mechanics that I was going to discuss, the so-called many minds theory. So David Albert discusses this in his book in chapter 6 after talking about the problem for the many worlds theory. The many minds interpretation is similar to the many worlds theory, except there's only one physical world in this theory, but there are many different consciousnesses. So the mind associated with a particular physical body splits whenever an interaction occurs that correlates the physical state of a system that's in a superposition with the observer's mental state. Right, so if you do an observation of a particular property on an object, and the object is actually in a superposition of different states for that property, then the world will split into different, or your mind will split into different minds, where one mind sees one measurement outcome and another mind sees the other measurement outcome. So it's like the many worlds interpretation, except there's just a large number of minds instead of a large number of physical worlds. Now this solves the preferred basis problem. The preferred basis is in terms of the observer's mental states, right? So in other words, it's your mind that cannot be in a superposition. There's always a definite state for each particular mind. Okay, now concluding thoughts about these interpretations. So all of these interpretations are motivated by problems with the collapse postulate of the Copenhagen interpretation, and they do indeed avoid the major problem with that. The major problem being that the collapse postulate implies a special role for observers and thereby raises questions about what's so special about observers or measurements or whatever it is, and raises questions about what exactly is meant by a measurement. So these interpretations do address that. However, they do not avoid what you might think is the more fundamental problem with the Copenhagen interpretation. This is the logical or conceptual problem with the idea of superposition. Because all of these interpretations allow there to be superpositions of particular states. So you can have an electron which is definitely within a certain region, but not in the left half and not in the right half, right? Which looks like a kind of logical contradiction. More generally, you can have something which definitely has a certain property, but does not have any particular value of the property. That's the idea of a superposition. And so none of these interpretations really deal with that problem.